Well, welcome to our lesson on the end behavior of a polynomial function. And I brought in two of my closest friends to help introduce the topic here tonight. And basically, throughout the night, we're going to be answering this very informal question. We said, where are the arrows? Where are those arrows on the ends of the graph taking us? So tonight, it's all about focusing on this end of the graph. We'll call this the extreme left. And then we're also going to focus on this side of the graph. Where is the extreme right side taking us? And throughout the night, we're going to be focusing on things like this. Is the leading coefficient positive or negative? In this case, it's negative, and we're going to show you tricks on how to figure that out. And also, we're going to keep asking ourselves, is the degree of the function an odd degree or an even degree? And basically, the combination of being able to answer those two questions is going to help us sort these graphs out. Now, again, it's all about the end behavior. We could basically just scribble out this whole middle section. We're only worried about what's happening here and what's happening here. So let's do a little bit of intro to our notation here. And let's see. I'm going to start with the far right side. As I move this way on my graph, we say that x is approaching infinity. Okay? While I'm doing that, this graph is heading south. And so we say f of x is approaching negative infinity. Notice how I'm using, every time I use that arrow, I'm using the word approaching. Let's jump to the other side. As I walk this direction, we would say that x is approaching negative infinity. Okay? And while I'm doing that, you notice how the graph is going up. So we would say that f of x, in this case, is approaching positive infinity just because that's going up right there. Okay, on the last slide, I kind of called that my informal definition, where we asked ourselves, where are the arrows on the ends of the graph taking us? Well, on this slide, we're going to cover what I call a more formal definition, and we're going to say that the end behavior of a function is a description of what happens to the values of a function. Okay, or sometimes values, we're referring to the y-coordinates, that's another way of saying it, of the function, as two things happen. Number one, as x approaches positive infinity and as x approaches negative infinity. And so that's really what end behavior is all about. End behavior says, I don't care what's happening when x equals 1 or when x equals 2 or when x equals negative 6. I want to know what's happening as x approaches positive infinity and negative infinity. Here's a beautiful diagram to copy down, and I think this is going to be a great diagram to kind of flip back to later in the year, a month from now, 3 months from now, 6 months from now. And it's going to really summarize this whole concept of end behavior. It's a slightly different graph than the one we opened up with on the first slide, but the notation is very similar. And so focus in on, as you're drawing this graph here, focusing on this section right here. We're saying as x approaches infinity, in other words, I'm traveling to the right. The graph itself is traveling upwards, so we said f of x approaches infinity, positive infinity. And then on the far left side, we say, okay, as I walk to the left, in other words, as x approaches negative infinity, what's the graph doing? What are the y-coordinates doing? And we would say they're heading south. F of x is approaching negative infinity. So this whole phrase, as x approaches infinity, can be described as the process of repeatedly substituting larger and larger positive numbers for x. And each time you do that, you're evaluating the function f of x. So it's like, what's f of 1,000? And then you're like, what's f of 1,000,000? And so forth as we get closer and closer to infinity. Now, before we can go any further talking about end behavior, we first got to review what does it mean to identify the degree of a function. And we've had some really hard ones lately, so I'm going to introduce you, warm you up with some easier ones. And first, our definition, we say a polynomial is said to be of degree n if the largest exponent in standard form is n. Okay, and I think standard form's the key because a lot of the ones that I've given to you so far this year weren't in standard form, which made it harder. So we're going to start off with some ones that are in standard form. So for me, this equation right here is in standard form. Everything's multiplied together already. You could think of standard form as being the opposite of factored form. And as you scan this polynomial, you'll notice the largest exponent is right there. So I'm going to say the degree is this is a third degree polynomial. Number 2, what's the largest exponent you see? It's a 5, so this is a 5th degree polynomial. And one more thing. If it's a third degree polynomial, we say it's an odd degree. Now there's a mixture of some odd terms and there's also some even terms in here, so the polynomial as a whole is neither odd nor even, but it's an odd degree polynomial. And of course this one, if n equals 5, that's also an odd degree polynomial. Okay. Let's see here. Number 3, the largest exponent is an 8, so I'm going to say this is an 8th degree polynomial, or in other words, it's an even degreed polynomial. Now here's where number 4 is the first one to get sneaky. This one's not in standard form, okay? I repeat, not in standard form, and what it is it's in factored form. So you have to ask yourself, if I multiplied it together, x times x would generate the first term being x squared. Now, I don't care what comes after x squared because I know every term after that is going to have a smaller exponent. So I'm going to stop right there and I'm going to say this is a second degree or an even degreed polynomial. Okay, the next one, let's do x squared times x and then multiply that by x. And I think that's going to give you x to the 4th. Now, of course, more terms are going to come after that as I multiply these rascals together, but we don't even care about those because I guarantee you that every exponent is going to be smaller than a 4. So let's say this is a 4th degree polynomial, or in other words, again, it's an even degreed polynomial. All right, let's see if we can get one more under our belt. What if we multiplied x to the 5th times x to the 3rd? That right there would give me x to the 8th. And then if I multiplied that there by x to the 10th, that would give me x to the 18th. And I guarantee you every term after that would have a smaller exponent. So let's call this an 18th degree polynomial, or in other words, again, it's an even degree polynomial. Okay, we're going to break our polynomials into 4 different groups, okay? And our first group is a polynomial with an even degree and a positive leading coefficient, okay? The best, friendliest example I can think of is f of x equals x squared. And first of all, it's a degree 2, so it's even degree. And my leading coefficient right here is an invisible 1, and it's a positive 1. And what that's going to do, of course, my graph looks like what? It's going to be a beautiful parabola whose vertex is sitting right on the origin. And what you're going to notice here is that as x approaches infinity, f of x is heading up, or it approaches infinity as well. On the other side, we'd say as x approaches negative infinity, f of x is going up, so f of x approaches infinity. And really, I'll tell you what, if you can identify whether the arrow's heading up or down, you're going to be in pretty good shape tomorrow. And so this is, we're just going to get used to using these little miniature arrows, and we're going to get used to pronouncing them as approaches and things like that. So basically, every even degreed function with a positive leading coefficient is going to behave the same way. Now, it might look a little different, but the ends are going to behave the same way. Let me make up something really wild. Okay, so let's say here's a crazy function. Notice how both ends are going up. In other words, it starts high and it finishes high. Well, guess what? This is going to be an even degreed function with a positive leading coefficient. And so what happens is it always starts high and it finishes high. Okay? And they always have that in common. Okay, again, we said we're going to break all of our polynomials into 4 categories. Here's the second of those 4 categories. So I'll put a little 2 here. We're still talking about even degreed functions, but now we're going to talk about what happens if the leading coefficient's negative. And we've seen this a little bit with parabolas in the past, so I bet you know what's coming. So that's the simplest one that we could talk about is negative x squared. So here's what's cooking. Our biggest exponent's a 2, so that's what we call it a second degree. It's an even number. And our leading coefficient is a negative 1, aka negative leading coefficient. So what does this graph look like? Alright, it's basically just a reflection of the last graph getting reflected over the x-axis. And let's talk about the end behavior here. As I walk to the right, in other words, as x approaches infinity, the graph is heading down, so we say f of x is approaching negative infinity, okay? What if I go to the other end? If I say, okay, x is approaching negative infinity, we're walking to the left, what's f of x doing? F of x is going down again, so let's say f of x is approaching negative infinity. One way to kind of summarize this group of functions is to say, you know what, it starts low and it finishes low. Starts low, finishes low. And that's going to be true anytime it's an even degreed function with a negative leading coefficient. Here's our third group, and this is the first time we're going to talk about an odd degreed function. And in this case, the leading coefficient is going to be positive. So let's say y equals, you could say f of x equals positive x cubed. So this is a third degree polynomial with a positive 1 as its leading coefficient. And what you're going to see happen here, whoops, I gotta grab my pen, there we go, is this particular function is going to climb like this. Notice the difference in this function. It starts low, but it finishes high. So that's the first time we'd seen that here. So let's describe the two ends. As I walk to the right, in other words, as x approaches infinity, the graph's going up. So we would say f of x approaches infinity. Now on the flip side, as we move to the left, as x approaches negative infinity, the graph's going down. So f of x is approaching negative infinity. So how do we want to generalize this group? And this is true anytime it's odd and positive, is we're going to say if the graph starts low, it's guaranteed to then finish high. Okay, start low, finish high. Start low, finish high. Alright, we're cruising right along, cruising. Here's our fourth of 4 categories. And I promise you, every single polynomial that we encounter is going to fall into one of these 4 categories. So now let's do odds with a negative leading coefficient. Something like this, negative x cubed. So this is a third degree polynomial with a negative 1 as its leading coefficient. And let's see, this graph is going to behave like this. Alright, and what you'll see here is the function starts high, but it finishes low, just the opposite of the last one. So let's go through our notation. As I walk to the right, x approaches infinity, but the graph heads south, or in other words, f of x approaches negative infinity. As I walk to the left, x approaches negative infinity, but the graph goes up, so f of x approaches positive infinity. Generalize this, we say if it starts high, it's then guaranteed to finish low. Start high, finish low. Start high, finish low. And that's going to be true for every odd function, odd degreed function with a negative leading coefficient. Okay, now we're going to take a brief detour. Our topic tonight was the end behavior of a polynomial. But I want to do some really advanced pre-calc work here for the next few seconds. And I'm going to talk about the end behavior of a rational function. And I think it's a little bit exciting to know that not all end behavior is limited to either positive or negative infinity. For me, that gets kind of boring because it's like we're either talking about positive infinity or negative infinity, and that's it. After a while, it gets pretty boring. So what I just wanted to prove here is that there are other types of end behaviors, and what we're going to do is we're going to introduce you to something called a horizontal asymptote. It's kind of like an invisible fence. we've got one to keep our goofy golden retriever in the yard, and it's almost like this invisible fence kind of keeps the function in a certain area. And you'll see the same thing over here, kind of traps the graph. But so let's say as x approaches positive infinity, this graph, it's neither going up nor down. What it's doing is it's approaching 3. So, it kind of spices it up a little bit, knowing it's not always going to be positive or negative infinity. But on the flip side, on this side of the graph, down here, we'll put an arrow there. As x approaches negative infinity, now the graph is going down. So we would have said, just like on our previous examples, that f of x is approaching negative infinity. On this next graph, let's talk about the right end, and then we'll do the left end second. As x approaches infinity, f of x, it's neither going up nor down. What it's doing is it's approaching 1. Let's go talk about the other side here. As x approaches negative infinity, f of x is, again, it's neither going up nor down. It's approaching 1 again. And we're going to see all sorts of crazy functions down the road as we get into higher levels of math. We'll see function, maybe there's a horizontal asymptote at y equals 4, and then there's another horizontal asymptote at y equals negative 3, and maybe our function does something crazy like this. So you've got these two invisible fences, and we could talk about the end behavior where f of x approaches 4 on this side and f of x approaches negative 3 on that end. Okay, we're going to get into some real live examples that we'll see tomorrow in the worksheet. And we're going to describe the end behavior without using our calculator, and we're going to focus on using appropriate notation here. So here's the key. Zoom in on this bear right here. That's really all that matters. As far as describing end behavior, these other terms are completely irrelevant today for the purpose of our discussion. This is a second degree polynomial. So if it's a second degree, we're going to say it's an even degree polynomial. And the leading coefficient is a positive 1. I'll put LC equals 1. The most important thing is that it's positive. Basically, so try to figure out which of the 4 categories that fits in. I think that's the very first one we did. And if you remember, the graph that we drew kind of looked like this. So we're going to say, whoops, oh my gosh, I almost started doing some calculus there. Oh, baby. Okay, not using the word limit. Okay, as x approaches infinity, f of x, I'm going to squeeze it in there, approaches infinity, because that's going up. And then as x approaches negative infinity, f of x again approaches infinity. In other words, both ends are going up. We say we start high and finish high on those types of functions. Okay, next function here. Let's see. Focus on this term right here and basically just throw these other terms in the garbage. They do not influence our answer. So what we've got here is an even degree. It's 4th degree. However, this time the leading coefficient is a negative 5. It's a negative number. So that's going to fit case number 2 that we studied. And the picture that we drew kind of looked like this shape. In other words, it started low and it finished low. So let's say the limit, oh my gosh, I did it again. I'm not using the word limit. Okay, as x approached infinity, which is this side, f of x approaches negative infinity. And as x approaches negative infinity, f of x also approaches negative infinity. Alright, next function. Let's focus on this bear right here, and we'll totally just ignore the 1. So what we've got here is an odd degree function, and the leading coefficient is a positive 2. So let's see, that's going to remind me of the third case. And we said in this case it started low but it finished high. Start low, finish high. So let's say as x approaches infinity, f of x approached infinity, and that describes that side. As x approached negative infinity, f of x went down, so it approached negative infinity, and that describes that side. Okay, last one. This bear right here, ignore everybody else. These are just distractors. They're just going to throw them in to try to throw you off your game. Let's see, we've got an odd degree because it's a 5. And the leading coefficient is a negative 1, negative number. That reminds me of the fourth case we studied where the graph started high but finished low. Started high but it finished low. So let's say as x approaches infinity, f of x goes down. It approaches negative infinity. That's that side right there. As x approaches negative infinity, the left side, then f of x goes up or approaches infinity. That's that side. Okay, this one's going to be a little overwhelming on the surface, but holy smokes, it's going to be easy, I promise. And it's just, I don't mean to diminish the question at all, but man, that is just a lot of blah, blah, blah up here. You know, the Center for Transportation Analysis, the CTA, studies all aspects of transportation in the United States, from energy and environmental concerns to safety and security challenges. I'll tell you what, I bet they make good money. A 1997 study compiled the following data of the fuel economy in miles per gallon of a car or light truck at various speed measured in miles per hour. The data is compiled in this table below. Well, what we did is we took all this table and we threw it into a scatter plot. So, for instance, pretend that 15 is your x value, pretend that 24.4 is your y value, and we plotted them as a point, and that's this point right here that you see. And then we did 20, 27.9, and that's this point, and this is what we call a scatter plot right here. Okay, I bet you did plenty of these in Algebra 1. So there's your scatter plot. The first question is, who's the independent variable? In Algebra 1, we talked about how x is the independent variable, and then we would have said y was the dependent variable because the value of y depends on what x is first to begin with. But really, the question that we want to get to today, as we catch up to speed for today, is right here. When you look at this data, if it was to be modeled by a polynomial function, determine if the function that models it would have an even or an odd degree. Now here's what I'm picturing. If I drew what I call a best fit curve, my best fit curve would look a little something like this. It's got a little wrinkle at the top, but it looks like this. Notice how it starts low and finishes low? That tells me it's even. Okay? Now, of course, the next question is, would the leading coefficient be positive or negative? Now, in this case, because we start low, finish low, I'm saying that the leading coefficient is negative. Okay? So really, I mean, there was a lot of wording, there was a lot of blah, blah, blah. We introduced you to a scatter plot, but all it is being able to visualize what the best fit curve looks like and being able to say, you know what, it starts low, finishes low. Okay, here's our wrap up for tonight, and we're going to try to describe some more graphs, and we're just going to practice determining whether it's odd or even, degreed, and whether the leading coefficient is positive or negative. And if we can answer those two questions, we are going to be lights out tomorrow. So, okay, let's get our kick started. This function here, degreed. Well, here's the deal. One end's going low while the other end's going high. Start low, finish high. That is odd. Okay. Now, if it starts low, finishes high for an odd function, then we say the leading coefficient is positive. In this case, if x approaches negative infinity, they're referring to this side. We're going down. So we could say y approaches negative infinity. And this y that they're using is the same thing as the f of x we've been using all night. And then if x approaches positive infinity, y approaches positive infinity as well. Okay, let's go get this bear over here. What we got here is we start high, finish low. And to me, that is, again, another odd function. Basically, if the two ends are opposites of each other, it's going to be an odd degreed function with a leading coefficient that is negative. Let's see, as x approaches negative infinity, y approaches positive infinity. That's this side. And as x approaches infinity, y approaches negative infinity. Get my negative in there. And that's this end right here. Let's see if I can find another color. Let's grab some purple. Okay. Let's see. Start high, finish high. That is an even degreed function. And I got to be careful. This one's not only even degreed, but it is an even function itself because it is symmetric with respect to the y-axis. The leading coefficient is positive, and we're going to say both ends are going up. So y approaches